In this video, we are looking at some very important properties of complex conjugates. Let's say we have a complex number, a plus bi. We can define a new complex number called its conjugate and denote by adding a little star to the top right of our complex number, which has the real part the same, so a, and the negative of the imaginary part. So this is a new complex number. And the first important thing we want to look at is that if we have a complex number set and we decide to find its conjugate, and then we decide to find the conjugate of the conjugate, actually we get back our original number set. Why is this? Let's say that set is a plus bi. So do we do this a lot? Saying when we have a complex number, just write it as imaginary part plus, real part plus imaginary part I, as a strategy to do the operations we want. So if this is set, we want to find the conjugate of this, and then we want to find the conjugate of the conjugate. And we want to see that we go back to the original number. The first time we find the conjugate, we are changing the sign of the imaginary part. And the second time we take the conjugate, we are changing the sign again. And because minus minus is plus, we want back to our complex number as we want. So apply 2 times this operation is like not doing anything. Second thing we want to notice is what happens when we sum a number plus its conjugate. So again, let's assume that our complex number is a plus bi, and I want to sum a plus bi plus a minus bi. That's the conjugate. So I'm going to have 2a for the real part, and then the imaginary parts are going to cancel because they have opposite sign. So the result is actually a real number. Another way of obtaining a real number is to multiply a number and its conjugate. We have done this before. If we say that our complex number is a plus bi, then when we want to write the complex number times conjugate, we have a plus bi times a minus bi, and that is a squared plus b squared. And this is a real number. We have already noticed that this is a real number, and also remember that this is second quality we have over here is the sum of two squares factorization. Just we're looking on the opposite from the usual way at this equality, but of course it's the same. Okay, what else? We want to also look at what happens when we do operations with numbers and their conjugate. Let's say we have two complex numbers, Z1 and Z2, and we wish to sum them, and we want to find the conjugate of the sum. And the property that we have is that this is actually the sum of the conjugates, so we can change the order of those operations. Instead of first summing and then finding the conjugates, we can find the conjugates of each of them and then sum. Actually, this property over here also holds if instead of summing we're subtracting the complex numbers. And let's see that this is true. Okay, I've made a bit more space, so let's look at the first of the properties, that the conjugate of a sum is a sum of the conjugates. The strategy is going to be the same as for the other two properties that we check. We are going to write each of these complex numbers in the form real part plus imaginary part times I. So I'm going to say that Z1 is equal to a plus bi, and Z2 is equal to c plus di. And now I'm going to do the operations on the left-hand side, and I'm going to write them so that actually we get the result in the right-hand side. So I want to sum and then take the conjugate of those two complex numbers. So I have a plus bi, and I need to sum c plus di, and after I'm done with the sum, I find the conjugate. I'm going to sum the real parts, a plus c, and then I need to sum the imaginary parts, b plus d, that multiply by I, and I want the conjugate of all of this, so I need to change the positive sign in between the two terms. So a plus c minus b plus d multiplied by I. Yeah, I'm going to now write this as a minus bi. So I'm taking this and this part, and then plus c minus di. So I'm again splitting according to which one of the complex number this is coming from. And this is actually the first one of my complex numbers, Z1 conjugate, plus the second one of the complex numbers, Z2 conjugate. And that was what we wanted to show. The proof for the difference between Z1 and Z2, it's very similar. We just need to change the sign, so I'm not going to write it down. Property, we are going to look at what happens when we multiply or even divide complex numbers. I'm going to multiply Z1 and Z2, and then if we find the conjugate of this will be the same as first finding the conjugate of each of these complex numbers and then multiplying them. And similarly, if we are dividing Z1 by Z2 and then finding the conjugate, we will obtain the same result if we first find the conjugate of each of these numbers and then we divide. Here I need to add the condition that the complex number Z2 cannot be equal to 0, so we can actually do the division. This is not hard, it's just a little bit more involved with the writing of the operations. I'm going to do the part with the multiplication. The one with the division is similar, and one more time. This is the strategy we have here, and it's a very important strategy. Let's write Z1 as a plus bi, and let's write Z2 as c plus di. Yeah, here a, b, c, and d are real numbers, so I'm just writing the complex numbers in the usual form that we know. And now let's start with the left-hand side, multiplying those numbers and finding the conjugate. So we have a plus bi, and we multiply it by c plus di. We'll find the conjugate afterwards. For the product, we are going to have AC minus BD for the real part, and then for the imaginary part, we are going to have AD plus BC, and all of that is multiplied by I. And we want the conjugate of this, so I'm just going to go ahead to write this and change the sign in front of the imaginary part. Now, this is actually what we want. It's just not very easy to see with so many letters A, B, C, D. But let's write what will be Z1 conjugate multiplied by Z2 conjugate, and we'll see that this is exactly what we got. We are going to have A minus BI, that's the conjugate of the first complex number, and that needs to be multiplied by C minus DI, the conjugate of the second number. And when we do so, we are going to have AC, and then we are going to have minus BD for the real part. So we have two negative signs, they cancel, but then we have I squared, so that's why we have a negative sign there. And then for the imaginary part, we have minus AD, and we also have minus BC. So both terms are with a minus sign in front and multiplied by I. But this is exactly what we got, because we can take the minus 1 as common factor of the imaginary part. And this is exactly what we want. Now, for the last part, we want to show that if we consider the n power of a complex number Z and then that's going to be a new complex number because we're just multiplying. Let me say here first that n is a positive integer. So we are just multiplying a complex number set by itself n times, and then we are taking the conjugate. This is the same as first taking the conjugate of z and then considering the n power of it. Quite a few things to comment over here. I say that n is a positive integer because that's the case we know for sure what it means z to the power of n. If it was a negative integer, we could also find the meaning of z to the power of negative n. Remember that we did an example with z to the power of negative 2. It will be just more involved. And if we were talking about non-integer values, then we will need to know how to take roots of complex numbers. And we don't know that yet. So I'm not saying that this property is not true more in general. I'm just saying that what we can do so far is to prove it in this context. First of all, if n is equal to 2, this is already proved. We did it in 4, so we saw that if we multiply two complex numbers and then we take the conjugate, then that's the same as taking the conjugates first and then multiplying them. So this is a particular case of what we just proved. Now, we know it's true for, well, obviously this is also true for n equals 1, right? Because in that case, we're just saying that z conjugate is equal to z conjugate. But we want to prove it for positive integers, and we're so lucky that we have a fantastic method to prove properties for positive integers. Yes, mathematical induction. So we have our base case, which is n equals 1, which is trivial, and we are going to write the rest of the mathematical induction because why not? That's always good to practice. I just need more space. Let's assume now that the property is true for some value k. So we are saying that z to the power of k conjugate is the same as z conjugate to the power of k. This is our inductive hypothesis, and we want to prove that it's true for k plus 1. So prove true for k plus 1. So we want to say that z to the power of k plus 1 conjugate is the same as z conjugate to the power of k plus 1. So let's see, let's start with z to the power of k plus 1 conjugate. This is z to the power of k multiplied by z. This is the conjugate we want to find. But by property 4, if we are multiplying two numbers and taking the conjugate, we can change the order and write that this is zk to conjugate multiplied by z conjugate. So I say for these two complex numbers, z to the k and z, multiplying them first and then taking the conjugate is the same as first taking the conjugate and then multiplying. But now for the first factor, z to the k conjugate, we can use the inductive hypothesis. So this is the property over here. It says that we can first consider z conjugate and then the k power of it, and we are multiplying that by z conjugate. So what we are doing over here is actually z conjugate to the power of k plus 1. And that was exactly what we wanted to prove. So now the last step of our mathematical induction is to write the conclusion. Since the property is true for n equals 1 trivially, and assuming it's true for k, we proved it's true for k plus 1. By the principle of mathematical induction, the property is true for all positive integers, and that was the last property we wanted to prove.